of Dash.
Right.
We have Chin here filming the whole thing. He is the Android engineer. Next to him is Jeff, our iOS engineer. So before getting into why we are here talking about geocaching, let's take a few minutes and let me tell you what we do at Dash, so you have a little bit of context of the problems that we're trying to solve and why we're working at Dash. So what is Dash? At Dash, we are building a connected car platform. So what we do is we tap into this spec called the onboard diagnostic spec that since 1996, any car that was manufactured in the US and in Europe, any car that was manufactured since 2001 has to comply with it. So all these cars come with this port. So what you have to do is you have to purchase this OBD dongle that you can get from Amazon, eBay. If you go on our website, we have a suggested list of devices that we recommend. So you buy this device, you download our app. We have an app both on iOS and Android. It's for free.
I'll pass it around to you.
Yes, you guys can see it. So once you buy this device, download our app, you pair it with Bluetooth. The port, usually the OBD port, is around 2 feet near the steering wheel. So you plug it in, download the app, pair it, and then that's good to go. So one of the main things we did with Dash is once it's paired, it'll always work in the background. So it's not that you have to get into the car and launch the app. So we want a complete hands-free experience, right? Because you don't want Dash to interfere with your driving. So yeah, it usually takes 2 minutes to get the app up and running. So a couple of things that we've been doing with Dash is once you have the device up and ready, we collect amazing stats from your car, whether it's your fuel level, your engine temperature. We calculate to near precision your fuel efficiency, which, as most of you know, is very different from your EPA rating. So it's based on several factors, how you're driving, the health of your car. So we give you all that. We give you that in near real time. When you end your trip, you get a nice summary that you can then export. So, for tax purposes, you want to see how much money you're spending, how many trips you took. So we have all this information, and based on what kind of information you're looking for from Dash, there's parental controls. So if you want to know where your kid is, not where your kid is driving, that would be a little bit too big brother. But if you want to know that your kid is not driving in a neighborhood that you don't want them to be driving, you can set geofence alerts. So if they are in a particular neighborhood that you told them not to drive, you'll get real-time alerts. We also give you audio alerts anytime you're speeding or we think you have a low fuel level. So we make it pretty interactive, and again, it's all hands-free. So based on all these amazing feature sets, let me just segue into how do we do these. So we honestly did all this because of AWS. It's a small team, as you can see, and building such core feature set would have not been possible without using an AWS stack. So let me give a little bit of overview of what we are using extensively from AWS. So let's start with DynamoDB. DynamoDB, how many of you here have used DynamoDB? All right, a few of you. So DynamoDB is a NoSQL solution for all of you that know, provided by AWS. It's a fully managed solution, so you don't have to worry about installing it, upgrading it, or scaling it. It has a really clear-cut feature of read and write throughput. You can maintain and manage how you do your read and write throughputs by adding CloudWatches, which is another alarm framework that's provided by AWS. DynamoDB provides almost single-digit millisecond latency for reads, so it works perfectly for our case. The second thing that we use is Kinesis. So again, Kinesis, I'm not sure how many of you have used it, but think about it as a big data pipeline that you can just pump lots of events to it, and then you can have isolated applications that are listening to this pipeline and doing things. So one of the main differences between Kinesis and your standard queue is in a queue, it's first in, first out, and if you have a client listening to a message in a queue, that gets popped out of the queue. In Kinesis, anything that's being pushed to the stream stays in the stream for 24 hours. So you can have applications that are scaling and doing multiple things with the same event. So I'll give you an example. we get tons and tons of OBD readings from a car, right? Every second we are pulling your speed readings, your fuel level readings, your engine readings. All these things are getting pushed to our Kinesis stream. And then we have these isolated applications. One of those applications job might be, hey, is this a fuel level reading? Let me see if the fuel level is low so I can generate an alert. The other one is, oh, it's a fuel level reading. Let me persist it to the database. So this is how you can write really powerful applications but have such nice decoupling. So it's easy to troubleshoot, it's easy to scale. So we really love Kinesis. Third is SQS, which is a simple queue service provided by AWS. How we use it is as a dead letter queue. Anything that happens in our application that causes an exception gets pushed to this dead letter queue. And that's great, because what we do is we set up cloud watches on these dead letter queues. So anytime there's any message in this dead letter queue, the team gets a notification and then we act right away. So this is great than just like putting it in a log file and sending emails out. Then we have Elastic Cache. Amazing. Elastic Cache is a fully managed caching solution provided by AWS. We use the Memcache implementation. So the cost of using Elastic Cache is significantly lower than Dynamo. So a lot of times people use caching because, round trip to the database costs time. Latency is the problem. But like I said, Dynamo latency is not your problem. So why would you need Elastic Cache? We're using Elastic Cache to save money. It is amazingly cheap to use Elastic Cache. And again, it's a fully managed solution. So if you want to scale it up or down, you want to upgrade it, all handled by Amazon. So that's been really great for us. CloudWatch, I again spoke about it a little bit. We have CloudWatches on all our Dynamo tables, SQS. So we have CloudWatches set up on provisioning. If we're doing reads more than we would like to, writes more than we like to, we get CloudWatch alarms. And then last but not the least, machine learning tool. This is something we started playing with about a month ago, and when Amazon released it, and this is pretty big for us. So it's been 18 months that Dash has been there in the Play Store, and we've been getting lots of data. And one of the main bottlenecks and one of the main limitations with our app is that you have to buy this hardware device that Brian was just passing around, the OBD device. Because we've collected data over 18 months, we can now do predictive analysis and start giving you predictions on your fuel efficiency and other such things based on all the data that we've already gathered. And this is a classic example of machine learning. But if we didn't have Amazon's machine learning tool, that would require us hiring a team of data scientists, hiring some sysadmins to keep that infrastructure up and running. So we literally eliminated all that need, and now we are just using Amazon machine learning tool and trying to come up with a Dash version that people can use without an OBD device. So if we can do that, that would be great improvement for us, a huge catalyst for us to grow and get more users. So enough of that. Now let's get down to why we are here. So based on all these features, there were certain features that really necessitated geoquerying. So one of those features is gas nearby feature. So gas nearby feature, most of you are familiar with, like GasBuddy has it. You want to see if there's gas stations nearby, and if there are, you want to pull them up and show it to the user. So in Dash, we have all the gas station data from the US, which is annotated by their lat long. So each gas station that we have has a lat long, and so now we want to be able to say, okay, you have this lat long, give me another entity that's in 20-mile radius of this entity. So clearly a case for geoquerying. We did use Mongo for it. We had Mongo going on just for this solution. It was working great, but let me go forward and then I'll show you why we transitioned. Then next came Dash and IFT integration. How many of you here have heard of IFT? Okay, it's a couple of you. So IFT is a great service. It stands for if this, then that. What it is it's basically a portal where you can have triggers and actions. So you can register your service and say, if a certain event takes place in this service, then do some other action in another service. So for Dash, it was amazing because you could say, oh, if my car is turning off mile before this lat long, which is my home, turn my thermostat, like Nest, on or off. Or if I am driving through this particular neighborhood, send a text to my friend saying, hey, I'm going to be there in 10-15 minutes. So there was a huge need and request coming in that, hey, because you guys are into Internet of Things of driving, we would really like to have that feature available in IF. So we actually worked with guys at IF to come up with a nice UI tool that let them put in some geodata. So now you can go in and say, okay, if I'm driving through San Francisco, that's a trigger. And the action could be send an Android text message to my friend saying, hey, I'm in your state now, and I'm in your city right now, and I should be there in 2 hours or something. So this was a huge, huge need for geoporting. How do you answer a question that a user is driving through a particular demarcated area? How do you answer a question that a particular car started and stopped in a particular area? So this was a way bigger need than just gas station nearby. Because gas station nearby could be an isolated solution that we were doing in Mongo, but this required pretty much a lot of our entities to now be annotated with geodata. So we started looking up at a few solutions that were out there. So the first one was Mongo, and we also looked at Postgres. One of the main reasons, it works great, there's no harm with Mongo, was that it wasn't our primary data store. So we are heavily invested in everything in Dynamo, and now you want to have a dupe, write, and read from Mongo, that would just be a nightmare. We didn't want to have to maintain 2 different data stores. Then second, it would require sysadmin tasks. Like one of the main reasons we like Dynamo is because it's a fully managed solution by AWS, and with a team that's so small and we have minimal resources, we didn't want to add on to more admin tasks and admin resources. And of course, as a programmer, there's so many coding costs. Now you write in code that's interacting between 2 different APIs. You have to spend time learning both of these systems in depth. It's already a lot of tasks understanding how one framework works or one solution works, and now add on another one. So we tried to steer away from that. Second one we looked at was Lucene. As you all know, Lucene is like the underlying framework based on which also many good famous search engines are built on, so Solr, Elasticsearch. So Lucene provides geospatial querying. But in our ecosystem, we could not justify adding a search engine. Like just because we wanted geoquerying, adding a search engine would mean like anyone if you work with search engines and it requires indexing. So what that would mean is anything that's going in our tables, we would have to take that record, run it through some transformer, and then index it in Lucene. So again, something similar to Mongo in terms of cost, we wanted to stay away from that. And last, but not the least, was Dynamo. So Dynamo is our primary database, and let's see what we can do for Dynamo. So I forget when they did it, Ryan, I don't know if you remember, but they released the
I remember, maybe a year and a half ago.
maybe a year and a half ago, right? Yeah, because it was before they released GSIs. So about a year and a half ago, we were just going through as many blogs as we could, and then we came across this amazing blog written by someone from AWS, and they released an open source library for geoquerying. That's exactly what we were looking for, so this was fantastic. So before we evaluate this library, I want to just give you a little bit of highlight on some DynamoDB terminology, because it's good that you get a refresher of DynamoDB terminology before we start talking about pros and cons. So in a DynamoDB, what's a hash? It's your primary key. So it could be anything. In our case, if you're keying things on vehicle, it's vehicle ID. If you're users, it's user ID. And your regular SQL word, it's an ID. It's a unique attribute. There's also another primary key, which is called hash range. So it's similar to primary key, but this is composed of 2 attributes. And the second one you can do a range on. So for example, you could have a vehicle ID as a primary key, and you could have a timestamp as a range. So what that can give you is ability to say, give me this vehicle ID, how many times was it in last week or last month? So you do time series queries. So you have a vehicle ID, you put just lets you do range queries greater than between equals. LSI, also known as local secondary index. So a local secondary index is an ability to come up with a secondary range to your already existing hash. So if your hash range was, let's say, vehicle ID and date time, you're like, oh, but I would also like to know for this particular vehicle ID, range of scores that they got in my system. So what you could do then is have an LSI on the score table, and that would become the range. So key thing here to keep in mind is LSI only gives you the option to swap all your range. You're still tied to the table's main hash. Then came the awesome thing, GSI, which was very, very, very new. GSI lets you have a completely external hash and hash range. So now if you're like, hey, I want to be able to query my data not just based on ID, but based on name, but I also want to keep the ability to be indexing on ID. GSI. Again, we want to have a GSI with range. You're like, okay, I want to query the table by name and also their score or something else. So you could have a GSI that's based on a different hash and a different range. So this opens up a lot of opportunities. Keep this in mind and then hello? Did you hear me all this time?
The AC just turned on. You're good.
Oh, it's like everyone's just staring. Okay. Keep staring. Okay. So now that we know the terms, let's look into how we evaluated the library. So library was great. It gave us the ability to create items, to query items that were geo-related. Wonderful. What were the things that really didn't fit our needs? First of all, it took away our table's hash and range. So the library required that whatever table you want your geodata querying to be done, your table's hash becomes the GeoHash and the range becomes the GeoHash range. Which was a big no-no for us, right? Because we wanted to answer queries like, okay, was this car stopped in an X mile radius? So we still wanted our hash to be vehicle ID. And with this solution, we just couldn't do that. Second one was it was developed prior to GSI. So when this library was written, they didn't release global secondary indices. So the only way to do this was local secondary indices. And if you remember, local secondary indices means you can have a secondary range, but you're still tied with the hash of the table. So you'd still be tied with the GeoHash as the table. So again, it doesn't solve our needs. Third one was, and these are all caveats that they actually, it's not something that they tricked us into. These are caveats that they released and they talked about it in their documentation. The last one was no solution for composite. Stopped in an X mile radius, that's all you can get. But you can get a vehicle car stopped in an X mile radius and the event was the car was turned on or turned off, or give me a venue in an X mile radius whose category is restaurants. So you couldn't do that in that solution. So then we were like, oh my god, it looks like we have some work to do. So then back when I looked like a small white boy wearing the blue eyes, I forked the library and was waiting for some lots of coffee. And then we ended up forking the library. So what did we do? So we took a step back and we're like, okay, what is a GeoHash, right? So GeoHash is this amazing encoding of latitude and longitude written by this guy, Gustavo Niemeyer. So if you go to geohash.org, you can type in latitude and longitude and it gives you a geocode. So what's amazing about this geocode? So what this geocode does is it gives you arbitrary precision on a particular location. So in my mind, I think about it as zooming in and zooming out of a map. So this is where I'm going to use a whiteboard. So let's say Mr. Gustavo said, for this building that we have a presentation at, the geocode is 865437999, right? The way he comes up with this is one lat long. If I start shaving off numbers from the right side of this particular index, I lose precision, but I start zooming out to a neighborhood. So now, if I'm interested in not just this building, I want to see my neighbors in this building. So I want to know about this block. So he's like, okay, you shave off these things, 8, 6, 5, 4, 3, 7. You're losing precision, but you're gaining access to a wider area. And that is amazing, because now you can do queries where you can be like, okay, you know, I have something with the prefix of 86547. Find me other places that have the same prefix. So this is the biggest thing that happened in GeoHash. The formula, the whole thing was actually written by Google. There were many papers on it that like now you can take a lat long and index places. And that's something that's been fully tested. We didn't write that, we just wanted to leverage that. And that's what the original Geo library was leveraging. So keeping this in mind, what are the different considerations that you have to keep in mind? So the longer the hash key is, the more precision you get. You're getting exactly that point. The shorter the hash key is, you're losing precision, but you're getting more results. So you have to filter more results in memory, right? What else do you need to know? That's all you need to know. Okay, so let's go next. So this is actually a picture that I took from the original Dynamo Geo library. I really like this visual. So this is like Gustavo's papers, the like description in nice picture form. So let's take our planet, right? So it's a sphere. Let's put it in a box. So it's a cube. So you have 6 planes there. So now let's talk about one plane. So you have plane A here. So if I take that plane A and I split it into cells, 1, 2, 3, 4. If there's any lat long here in A1, they all will share the prefix 1. If there's anyone here, they all will share prefix 2, 3, 4, and so forth. Let me go and, break it down, because now I'm getting more and more precise. So here it was 1, 2, 3, 4. I'm going to break 2 further down. So it becomes 2, 1, 2, 2, 2, 3, 2, 4. What does that mean? Everyone here has prefix of 2. Now I'm going to take 2, 2 and keep breaking it down further. So it becomes 2, 2, 1, 2, 2, 2, 2, 3, 4. They all now have the prefix of 2, 2. So you're seeing as narrow and narrower you're getting more and more common prefixes. And that's exactly what this was. So as you keep shaving it off, you start losing precision, and you start covering more area. As you start increasing the prefixes, you start narrowing down in the plane. Okay, so now all this theory, how does this actually come to the API and your usage, right? Because the idea is to keep it simple and to not boggle down people with these details. So what are the things that you need to keep in mind? 999. And that's great, right? Because that will give me both of these. So only one query gets fired. Awesome. What's the con of this? You get a lot of results, right? Because the shorter the query, the hash key length, lots of results you get. But the queries fired are low. Let's take the second example, hash key length 7. So now it's up till here. So what's that? 609.352.2000, and then 609.352.29999. That's not going to pick up because it's 2, 3. So then I have to go forward. So the second query would be 609.352.3000, and then 23999, and that'll pick it up. So the pros and cons you have to see, like one fires more queries, one fires less queries. There's more results in one, there's less results in one. So it all depends on how many resources you have available. Do you have more access to I/O? Do you have more memory? Do you have more CPU? So these are the tests that you have to do. Because somewhere you have to make a compromise. I mean, geoquerying is not easy on resources. Doesn't matter what solution you use, right? So these are the pros and cons you have to choose. Like, can I afford more? Maybe Dynamo, you have lots of money to spend on Dynamo. You don't really care about throughput. Or maybe you have really high memory and high CPU, and you don't care about getting lots of results in memory and filter through them. So those are the trade-offs that you have to keep in mind. So let's take a quick look at things that we provide in the API. So in the API, we provide methods to create and query geo items. So one of the things that I want to highlight here is our methods do not give you results. They will only use a decorator pattern. So what we do is we take the request that you provided. So if you provided us with a code item request, which is a low-level Dynamo request, we decorate it with all the geodata that needs to be there. And this was done on purpose. The reason being, you control how you want to fire your query. Maybe you have a different way of firing queries. Maybe you want to do batch loading. Maybe you have multi-threaded jobs. So we don't want to take that from users. And that was one of the reasons we were hesitant to use the initial solution, because we have our own way of firing these queries. Second is we support composite queries. So now if you want to say, hey, in a region 15-mile distance and has a property of this, get me that. That takes care of it. Again, this I already mentioned, you can have as many GeoHash columns as you need. So because it's hard to choose an optimal length, you don't know how you're recording your data, we give you the ability to have as many columns as possible, storing different GeoHash lengths and picking up which column you want as a hash based on the query coming in. So these are some of the things. So let's dive a bit deeper into how you save an item using our API. So the caller passes in the existing put item request. This is what I was talking about. So you actually pass us your lower level put item request, which is something that you would do if you were saving data into Dynamo. If you're saving data into Dynamo using their API, you create a put item request. So you just take that put item request and you give us the lat long, and we will then return. So you're passing a put item request and we are returning the same put item request. The difference is this put item request that's being returned to you now is annotated with all geodata. So then you can go ahead and save it the way you save it. You want to do bulk save, you can do bulk save. You want to have a large item persistence strategy. So Dynamo has a strict limitation on how big an item size can be. In Dash, our strategy is to save that item in S3, and that's one of the recommended approaches by Dynamo. So if an item doesn't fit, we save the S3 key and we save the whole item into S3. So things like this is great, that like we are not trying to solve things for you. We're just giving you, a query request object that you can then go and do whatever you want to do. But we will guarantee that your data will be saved. Yep. Now let's get into the querying part. So we provide the same queries that the original library was providing, which is, given a lat long, we can give you that back. Given a radius, which is you just give this lat long of the center and a mile radius. I think it's in meters. We give you that back, and rectangle we give lat long of the diagonals. Again, we don't give you the results back. We just give you the annotated query requests back, so you can run them however way you want. So here, so now query request object. That's the same object. That's the same object that you would pass if you were working with Dynamo API. So you pass us the same object, but because one query can lead to several 100,000 queries, right? Because depending on your range, your radius, your hash key, we give you back this GeoQuery request object, which is a wrapper of a list of many GeoQuery objects, and also a filter. So if you want to filter certain items, you can do that. So again, benefit of this approach, you have the option to fire these queries the way you want. You want to run them in a multi-threaded environment, you want to do a map reduce job, it's all up to you. We are just giving you annotated queries back. So finally, how can you help? We need your help. So please, please, please look at our GitHub page. Tell us how bad our documentation is so we can improve it. Fork our repo. It would be amazing if you can start playing with it and create some examples. What's missing from our GitHub page is some good examples, and I think that's when a lot of people get lost because they're like, okay, this is good, but how do I use it? And I'm sorry, didn't have time to add examples. example, so help us. Another one is, it would be great if we could have a solution where instead of leveraging global secondary indices that actually take over your main table, to externalize the geodata to a different table. And it shouldn't be really that hard based on, like, if you look at implementation, it's all done, it's all very configurable, right? It's just the name of the hash key and hash column and the index where they're coming from. So it should be fairly easy to do. We just didn't have cycles to do that, but if you could do that, we get you some beer. And last but not the least, this is a really tricky but amazing problem. So add support for double composition. So what we have done is, okay, we can give you composite keys where you can say, okay, vehicle ID is this, and range is this. So you have a range of X miles, and a category is this. What we would like to do is say also another composition of a range. So if a vehicle ID stop in an X mile radius in the last 10 days. So if this is a bijection problem, you're talking about another range that needs to be then computed and taken part into this. So you could come up with that solution, that would be awesome. And yeah, that's it. We're hiring. If you like what we talked about, talk to us. We'll be here, hanging out here for some time. We are a really small team, and we're looking for talented, passionate engineers, whether it's UI, whether it's iOS, Android, backend, data analysis, whatever. Come talk to us. We also released our API a couple of months ago, so if you guys are interested in knowing what kind of data is available from Dash, check it out, create some cool apps, tell us what you did, and visit our website and download our